lattice vibration से which just एक छोटा part सी phonon था, but it is again a very important part. That what do you mean by the phonon? उन तक ਤੁਸੀਂ सारे ने सुना होगा photon, जिसके विस्तार से लेके हमने the quanta of energy by which the energy will be transferred in small packets or energy bundles. But here we study the fact of phonon. Phonon is basically the quanta of energy in case of solids, that means in crystals, lattice vibrations. Actually, in case of a small crystal, the energy will be transferred by a very small energy bundle or energy quanta, which is known as the phonon. Same उसी तरीके नाल इससे behaviors है, जिਵੇਂ ਦੇ behaviors photon से which see it follows Bose-Einstein statistics. Bose-Einstein statistics में जे follow कर रहा है, that means it behave as a boson, not as a fermion. Is it clear? That means it follows Bose-Einstein statistics. ਹੁਣ क्वेश्चन एक माइंड ਦੇ ਵਿੱਚ ਆਉਂਦਾ ਹੈ ਕਿ ਫੋਨੋਨ ਦਾ ਕਨਸੈਪਟ ਆਇਆ ਕਿਵੇਂ, what are its evidences, ਕੀ ਪ੍ਰੂਫ ਹੈ ਕਿ ਫੋਨੋਨ ਨਾਮ ਦੀ ਕੋਈ ਚੀਜ਼ ਹੈ, ਫੋਨੋਨ ਦਾ ਕਨਸੈਪਟ ਓਕੇ ਹੈ, ਠੀਕ ਹੈ। ਤਾਂ ਇਸੇ ਲਈ ਅਸੀਂ ਲੈ ਕੇ ਆਵਾਂਗੇ ਸਪੈਸਿਫਿਕ ਹੀਟ ਕੈਪੈਸਿਟੀ ਆਫ ਸੋਲਿਡਸ ਦਾ ਕਨਸੈਪਟ। ਵੀ ਆਲ ਨੋ that at absolute 0 Kelvin temperature the specific heat capacity of solids also approaches to 0. It implies that as the temperature increases, that means lattice vibrations will occur, and as the lattice vibrations will start or occur, that means atoms to another atom or molecules, they will vibrate and the energy will be transferred, or you can say thermal energy spatially will be transferred in small energy bundles, and that is due to the just a phonon. And one important point is also there that phonon has no physical significance, but in actual outside the crystal space it has no any point or no any evidence, but within the crystal it has some physical significance. For example, it is basically occurs inside the crystal, that means momenta of crystals, but as we talking about the space, then it has no meaning, no sense. ਹੁਣ इसी केस के विचकार आगे से स्टार्ट करना है phonon or phonon photon scattering. Basically, when the concept of scattering is there, scattering is nothing but it is basically a collision. What it implies that when there will be a collision between microscopic particles, that means exact contact of the particles is not meaningful, but change in momenta or change in energy is meaningful when we are talking about the scattering. In this case, there are basically two types of scattering. One is elastic scattering and another is the inelastic scattering. In case of elastic scattering, we all know about that kinetic energy and momenta both remains conserved. That means these two things will be conserved. But when we are talking about inelastic scattering, that means kinetic energy does not conserve, but momentum will conserve. Similarly, elastic scattering in case of phonon is known as the normal process. This is known as normal process, and sometimes we say just a simple way end process. And inelastic scattering is known as unclamped process and also known as simply a U process. One by one we will talking about them. First of all, I am talking about the normal process or end process. In this case, what happens when one or two phonons will combine to generate a third phonon, that is known as the normal process. For example, I have two phonons and their wave vectors are k1 and k2. Both will combine to generate a third phonon, that is whose wave vector is again k3. is known as elastic process. In this case, kinetic energy and momentum of phonon before and after scattering will remain conserved. Also, in case of you can say momenta, we all know that momentum P is equals to h bar k, where h bar is equals to h upon 2 pi, which is known as reduced Planck's constant, and k is a wave vector or propagational constant. In this case, if I multiply by h bar on both sides, then h bar k1 plus h bar k2 equals to h bar k3. That means the momentum will conserve. And in case of conservation of energy, I can take that is E equals to h bar omega, where omega is the angular frequency and h bar is again reduced Planck's constant. If I take this factor, that means say omega 1 and omega 2, omega 3 are the angular frequencies of phonons before scattering and after scattering, then I can write h bar omega 1 plus h bar omega 2 equals to h bar omega 3. One important concept is there in case of elastic scattering, that resistance at very low temperature, that is basically equals to 0. If resistance is 0, that means thermal conductivity sigma is approaches to infinite. It approaches to infinity. Is it clear? And when we are talking about the case of inelastic scattering, inelastic scattering में which ਅਸੀਂ already ਗੱਲ कर चुके हैं, that momentum conserved but kinetic energy doesn't conserve. That means one of the factors from kinetic energy momentum will not conserve. If these are not conserved, then we have to apply some factors or do something to conserve it, because it cannot possible that momentum or kinetic energy will not conserve. To conserve these factors, I am just taking an introduction of the lattice points. Here, the concept of lattice points, that means interaction of phonon with lattice, and we again I can represent lattice points by the reciprocal lattice. Is it clear? We all have done in previous semester that the reciprocal lattice vector or lattice point is denoted by capital G. That means in this case, what happens? The phonon's energy, or you can say phonon's momentum, will be interact with the lattice points or reciprocal lattice vectors. Yeah? In this case, there are basically again a concept of 4 phonon factors. If K1, K2, K3 are the wave vectors of 3 phonons, and 4th lattice factor is represented by capital G, then I can say K1 plus K2 equals to K3 plus G. All are in vector forms. Okay. Now multiply by h bar, then h bar K1 plus h bar K2 equals to h bar K3 plus h bar G vector. That means the momentum will conserve. And in case of again energy, simply just multiply it by omega, where omegas are the angular frequencies of the phonons. Okay. After that, I am talking about the phonon-photon scattering. That's very important. Always in university exams, the question will asked by students, what do you mean by the phonon-photon scattering? In case of phonon-photon scattering, there are again 2 cases in which there is an emission of phonon, and in which there will be the absorption of phonon. Okay, Let us suppose simply I am taking first of all a case of lattice point. This point represents a lattice point. Okay. If this is a lattice point and I am just interacting it with a photon, then we all know about that photon is represented by this kind of wave. That is the representation of photon. But phonon is represented by like that. This is the representation of phonon. When a photon is interact, this is a photon, which is basically the incident photon. Now, incident photon is interacting with a lattice point, then it loses some energy. And when it loses some energy or scattered by the lattice point, then the scattered photon has different wave vector and different angular frequency. If I take its wave vector is k1, then its wave vector is say k1, or you can also write k or k dash. So this is k dash. Its angular frequency is say omega and its angular frequency is say omega dash. Then we all know that when incident photon is interacting with lattice point, some of its energy or momentum will change. And if there is the emission of phonon, if there is the emission of phonon, then I can say some of the energy will be released into the emission of a phonon. That means there is the concept of phonon which is emitted, and its wave vector is say capital K and angular frequency is omega by this way. Clear? And to represent the conservation of the momentum law, I can say K h bar plus K dash h bar equals to the lattice point, that is capital G, into h bar plus K, that is the wave vector of emitted phonon, then h bar into capital K. And in terms of energy, similarly, that is K, or you can say h bar omega, this one, plus h bar omega dash equals to h bar capital G plus h bar into capital omega. That's a different way. Okay? That means in this case energy will be lost and the emission of phonon will take place. Clear? If there is a opposite case, that means phonon will be absorbed. At that point, when I am saying that there is the absorption of phonon, in that case, what happens? Suppose again there is a lattice point, there is a phonon interacting with this lattice point. Here, and there is a photon which is again interacting with this lattice point, that is wave vector K, wave vector capital K, and another photon will be emitted, so that is K dash. Then in this case phonon will absorb. This concept of phonon is basically very important to recognize or to learn superconductivity, because in case of superconductivity you deal with the phonon, photon or phonon electron scattering. Now in this case what happens? K plus capital K is equals to this K dash, and if there is the involvement of lattice point, then it is also introduced, that is capital G. Okay, that means by these all factors or all parameters we can study or we can learn about the phonon or photon scattering. Clear? To represent this in a more analytical way, I just show you an example, or you can say a treatment, analytical treatment to make a relation with angles, that is scattering angle and phonon wave vector. For this, I am taking, let us suppose there is a incident photon with a lattice point, and some of its energy will be removed in scattered photon. This is a scattered photon. Clear? And the sum of its energy will be changes to a ejection of a phonon. That is capital K. That means incident photon, it strikes or scattered at lattice point, emission of scattered photon, and then phonon. Clear? But in Lewis equation, we all know about that the direction of incident photon is very important. For this, I am drawing the direction, that means in this way, which is the direction of the incident photon. And if the angle between the direction of incident photon to the scattered photon is represented by phi, and I divide this angle by a perpendicular bisector, then the angle becomes phi by 2 at above side and phi by 2 at lower side. Okay. Now this magnitude, say I take a triangle A, B and C, then the magnitude of the B to C is equals to the magnitude of the wave vector of phonon. Clear? For this calculation, can I write it as a point say D, and twice of B to D magnitude will be equals to B to C magnitude equals to the wave vector capital K magnitude. Clear? That means if I am able to calculate B to D, BD, that means I will also calculate the vector K, which is the phonon wave vector. First. Then in triangle of ABD, sine of phi by 2 is equals to perpendicular upon hypotenuse, that is B to D divided by hypotenuse A to B, and its wave vector is K dash because it is a scattered photon, and its wave vector is say K because it is an incident photon. Then BD divided by K dash, and K dash into sine of phi by 2 is equals to B to D. Multiply by 2 on both sides, then it is twice of B to D. And 2BD equals to B to C, which is nothing but equals to the magnitude of the phonon wave vector, that is capital K. That means K vector magnitude is equals to the 2K dash sine of phi by 2. Is it clear? Now we all know that it is also treated by the phase velocity. In this case, phonon is basically generated or transmitted by the sound waves. Clear? Because all these lattice vibrations are treated with the acoustical or optical branches, and acoustical branches is deal with the sound waves. For this, if I take the velocity of sound is say Vs, which is equals to one point is that is refractive index mu equals to C by Vs. Then Vs equals to C upon mu. Clear? Where C is the velocity of light, mu is the refractive index of the material, and Vs is the velocity of sound. That means the elastic wave velocity which propagates through the lattice. Clear? And this relation is also deal with the angular frequency. That is Vs equals to omega by k. You all know that phase velocity Vp equals to omega by k quantum mechanically. Then Vs is also equals to omega by k. comparing these two relations, then I can write omega by k equals to c upon mu, or k is equals to omega into mu divided by c. Put this value of k here. Clear? And one important thing, that the magnitude of k vector equals to magnitude of the k dash vector. Magnitude remains same of incident and scattered, just the direction will be changed. That means this factor becomes 2 into k dash, or k, that is equals to omega mu upon c into sine of phi by 2 equals to capital K vector magnitude. That's a very important relationship. By this is the end of the phonon concept. That's very important to understand the lattice vibration, quanta of energy, which deals with the elastic waves across the lattice or across the material. Thank you.